Hi and welcome to this clip going through the C3L6 2019 paper. This time we're doing question number 2. At the start of all my clips going through Cambridge Chemistry Challenge papers, I like to try and spend a minute or so just taking you through some of the information and guidelines on the front of the paper. So for example, although the paper is obviously going to be challenging, otherwise it wouldn't be called a Cambridge Chemistry Challenge, they try to encourage you to adopt a problem-solving approach, a deductive approach, rather than trying to remember lots of different materials from your course. Obviously you'll need to remember a few basics, like for example balancing equations, mole calculations, redox oxidation numbers, those kind of things, but there's nothing new that they'll be expecting you to have come across. They talk about reading around your subject, don't they? That doesn't mean you'll have had to have come across something special that other people might not have done in order to be successful in this paper. So provided you're open to doing some problem solving and deducing, you should be able to work your way through most of it quite logically. So we get 90 minutes. It's all the questions have to be done. You get an answer booklet and you give the essential steps in your calculations. So when you do calculations, make sure that the stages or the essential steps are laid out clearly so somebody can give you credit for it. Similarly with organic structures, don't do a little organic structure in a postage stamp sized space at the corner. Make some space for it and write it out clearly so someone can look at it and say, yeah, I know what that person's talking about. And finally, appropriate significant figures refer to the least sensitive as used or quoted in the question. If you're not sure, maybe stick to 3 significant figures. And they mention units, so be willing to use very large and very low orders of magnitude. So in other words, times 10 to the minus 10 in your calculator. Be comfortable and prepared to do that. There's no limit to how big or how small numbers can be, obviously. So you'll get a periodic table with your paper, and you'll notice that the relative atomic masses are often quoted to 2 decimal places as opposed to 1 decimal place, which you might be used to. So the level of precision of the numbers is higher, so therefore you need to make sure you use the numbers given here in your calculations as opposed to numbers you might remember from your use of your exam board's periodic table. The reason for this is the periodic tables from most exam boards at A level use 1 decimal place. So for example, chlorine being 35.5, that would be the first thing that comes into most people's heads, or calcium maybe 40.1. If you look at calcium and chlorine here, it's 35.45. You'd round it to 35.5, but it's 35.45 here. So obviously the first thing that grabs your attention is the picture of a lovely grey cat. And we're human beings, so who can't feel a little bit more relaxed and happy in the presence of such a lovely creature? So in the question, you'll see that the very first part has a paragraph that introduces sugars. And the context they're talking about is the use of periodic acid as a reagent for helping to determine which isomer of a sugar is present in a sample. So following the feline advice I've been given, periodic acid exists in 2 forms, orthoperiodic acid, H5IO6, and metaperiodic acid, HIO4. And it says that metaperiodic acid can be formed by heating orthoperiodic acid. So to look at the oxidation state of iodine in periodic acid, it doesn't necessarily say which of the 2 forms of periodic acid they want you to look at this in. So let's do both anyway. So if we start by assigning oxidation numbers to the elements we know the oxidation state of, namely hydrogen and oxygen. So by adding up the oxidation states of the individual elements that we know them for, we can work out that iodine in orthoperiodic acid must be +7. And if we do the same thing for HIO4, metaperiodic acid, we find the same thing. So part 2 asks you to write a balanced chemical equation for the formation of metaperiodic acid from orthoperiodic acid. periodic acid. I can't get the pronunciation right, can I? So the chemical equation for the formation of meta-periodic acid from orthoperiodic acid involves heating. So therefore that would be breaking bonds and potentially decomposition. So that might be two things produced from H5IO6. So if you change from H5IO6 to HIO4, you use up 4 hydrogens. So if you use these 4 hydrogens to make 2 waters, it also balances for oxygen, because the oxygen goes from 6 down to 4 in HIO4. So in the next part they want 2 structures, one for orthoperiodic acid and one for meta-periodic acid. So remembering that hydrogen commonly dissociates from oxygen in acids that contain oxygen, such as H2SO4, HNO3, examples that you've seen, I know that I can write quite a few OH groups on the iodine of orthoperiodic acid. But because I only have one hydrogen coming off meta-periodic acid, that means that I've got to be a bit careful how I write that. So it's got to be on an OH, and then the remaining bonds have to be iodine double bond oxygen. So in the next one, they're asking you to work out whether your periodic acid is acting as an oxidizing agent, a reducing agent, a dehydrating agent, or a catalyst in the reaction that they give you. So if we look carefully, you'll see that C single bond O becomes C double bond O. So this must be the creation of an extra carbon-oxygen bond. So this is an oxidation. So therefore periodic acid is behaving in this case as an oxidizing agent. So these alcohol groups are all secondary alcohols. So you have to think quite carefully about what happens. So first thing that happens is the cleavage of the carbon-carbon bond. Now they're secondary at the moment, but when you break the carbon-carbon bond, you have to think, do you have the primary alcohol in the remaining carbon structure? If that's the case, the alcohol will be oxidized by the periodic acid to an aldehyde. But it'll be a ketone if the carbon chain remains secondary. So I'll leave the arrows pointing at the carbon-carbon bonds that break, and you can follow me along as I put the structures in. So dealing with the first carbon-carbon bond breaking, now let's go to the next carbon-carbon bond that breaks. So on the right hand one, the part II, you get 3 products. And it says the reaction proceeds by first forming a cyclic intermediate species in which the oxygens of both alcohol groups are bonded to the iodine. So let's have a look of the structure that's formed when butane 2,3-diol reacts with periodic acid. So if we take butane 2,3-diol, so we draw the butyl chain first, and then it says the cyclic intermediate species in which the oxygens of both the alcohol groups are bonded with the iodine. So I need to make some room here, so I'll get rid of my butane 2,3-diol. I add my oxygens in, I connect them to the iodine, and finally we can add the periodic acid so that we form a ring structure, so we have a cyclic intermediate. So let's now move on to the next question, next section. So here it says that periodic acid reacts with other compounds, including some where a carbonyl group is adjacent to an alcohol. And the reaction has the same mechanism in molecules with 2 alcohols, and that's because aldehydes and ketones are in equilibrium with a small amount of a hydrate in aqueous solution as shown below. So then it asks you to suggest structures for the hydrated versions of aldehyde A and ketone B. So all you really have to do is change the C double bond O into COH2. So in other words, the 2 bonds to 1 oxygen becomes 2 separate bonds to 2 separate oxygens in 2 separate OH groups. And then it wants to suggest structures for the products resulting from the reaction of aldehyde A and ketone B with periodic acid. So remembering what the periodic acid does, it oxidizes the structures left once it's broken the carbon-carbon bond. Now the carbon-carbon bond has to be between two alcohols, or maybe between an alcohol and a carbonyl. So in this part of the question they're talking about the carbon-carbon bond between a carbonyl, C double bond O, and an alcohol. So they're taking the setting from earlier and changing its emphasis a little bit. So I've labelled up the aldehyde A and ketone B with what's going to happen. So if we separate the two compounds out, so you can see clearly which structures each one turns into. So in this question they're wanting us to consider 1,3-dihydroxypropan-2-one. And in its reaction with HiO4, which is obviously one of the periodic acids that we looked at earlier. Now when periodic acid reacts with this, hopefully what you'll be able to work out is that the first thing that will happen is the periodic acid will break those two bonds. So remembering it's a breaking of a C bond and then oxidation of what's left. That gives us those two products, compound C and compound D. So now we consider what happens to the product. This time we're looking at compound C. You can see from the reaction scheme it's still subject to reaction with HiO4. So again, C bond broken, and then the primary alcohol is oxidized. So we get compound D again. This time I have put in the whole displayed formula, not the skeletal formula like before. And that gives us also carbon dioxide. It's the only thing that's left over. So, now what we can look at is the next question. So they're asking us in part G to draw all of the carbon-containing products resulting from the complete reaction of glucose with an excess of periodic acid. It says you can ignore stereochemistry, in other words, optical isomers, but you could show the number of moles of each produced. So if there's two of something that's made, you need to put a 2 in front of it. So let's now have a look at all of the carbon-carbon bonds that are going to be broken in glucose. So if we take all of the indicated bonds, they'll fulfill one of the two criteria we've looked at for reaction with periodic acid. So what we need to do is break them. So that means that all the bonds break that are indicated, and anything that's left over that can be oxidized is oxidized. So we're going to need to take this in a couple of stages. So I'm going to call this cleavage and oxidation 1. I've got rid of one of the arrows. So I've got a methanol molecule and the remaining structure that was left from glucose. And I'm going to code each of the carbon-carbon bonds that break as 2, 3, 4 and 5. So each of them will involve a cleavage and oxidation. So what I'll do is I'll draw the products of what we've got left. Now the methanol is going to be left alone. So it's this molecule I'm now going to be working on. So you can work out what's going to happen now at 3, 4 and 5, because we've done cleavage and oxidation 2, and you'd get basically 5 of those molecules. So now we do the same for fructose. Exactly the same task, same approach, except this time I'm not going to annotate the diagram. I'm going to speed it up a little bit and just simply draw out the products. If you wanted to pause the clip, for example, and go back and have a look at working it out for yourself this time, that would probably be a good exercise. So you get 3 moles of methanolic acid, 2 moles of methanol and 1 mole of CO2. So moving on to part 8, it starts talking about fucose and fuculose. So it says that you add a phosphate group to one of the alcohol groups on fuculose, and it's catalyzed by the enzyme fuculose kinase. And when they discovered this metabolic pathway in 1962, they used periodic acid to determine which alcohol group becomes phosphorylated. So it says that fuculose phosphate was shown to react with periodic acid in a molar ratio of 1 to 3. And it asks you to suggest any structure or structures that are consistent with this observation. So let's take a moment to think about phosphorylation that they're talking about. So phosphorylation is simply the replacement of the H atom in an alcohol group. So you've got four possible alcohol groups that this could happen in on fuculose. And what happens, instead of PO4, you get PO3, but attached to that oxygen. So one of the hydrogens that are written on the OH groups, they'll come off and PO3 will come on. So in line with what the question tells us, this now are the 4 phosphorylation sites. The thing is, we need 3 molecules of HiO4 per single molecule of fuculose phosphate. So out of those 4 sites, we need to choose carefully where we put our phosphate group so that we still have the criteria for the HiO3 to oxidize the remaining parts of the molecule. So thinking about this, the criteria for HiO3 to attack or react is, first of all, a C single bond C, or a C single bond C between either 2 alcohols or between an alcohol and a C double bond O. So that now takes the 3 on the right hand side out of the picture. They need to stay where they are. So they've got to stay as OHs, so only the one on the left is phosphorylated. So we've got more than one possibility actually. So we need to think about where the carbon-carbon bond is broken by HiO4 and indicate that by a sort of red slash. And if you think where we can put the PO3, the phosphorylate part of the molecule. And those are the 2 possibilities we've got. And the final part, part J. The problem with J part I is we don't have enough data to even attempt to calculate the molar mass of the structure. So we have to take what we know about it and put it together. So the phosphorus containing product will contain this. The question tells you it's fully protonated, so we need to put protons onto those O minuses. The product of full oxidation of a primary alcohol on the end of fuculose would be, the primary alcohol that would be left behind, the aldehyde, beg your pardon, that will be left behind when the OH on the right hand side of fuculose is oxidized, get here in the end, is COOH. Structure. So its molar mass is 156.03 grams per mole, and therefore the carbon atoms are 24.02 grams of this per mole. So this gives us 15.4% by mass of carbon. So that will be our structure for part I. And it says, hence suggest the structures from part H that are consistent with this observation. So that gives you the phosphorylated fuculose, or fuculose phosphate. Now obviously I've taken the protons off because it would have been deprotonated once the phosphorylate group was on there, or phosphate if you want to call it that, but I think they accept the deprotonated or the protonated form. Okay, so that takes us to the end of this clip. Another tough one, I think. It took me a few hours to get my head around it and try and think how I'm going to explain it, so it's pushed me a little bit as well. So once again, thanks for listening if you got this far, and until next time, see you soon.